Welcome, subscribers. The views and opinions shared in this podcast are the personal viewpoints of the participants and may not necessarily reflect the stances of the Institute for Safety in Powerline Construction and staff. It is highly advised to consult your company management before implementing any actions or policy changes that you hear during this broadcast. And that's always good information for anything that you do. We can't rely on everybody to tell us how to run a power company or how to run a utility or how to do our training. We are ultimately, legally, and by OSHA responsible for being able to defend what it is that we do. So we do research and we take opportunities and we get to meet people in podcasts like you're going to meet today. And hopefully that's going to be too invaluable to you.
This podcast is sponsored by IP Institute. Develop your utility frontline leaders today at ip-institute.com.
Okay, we always start with a safety moment. So we're going to have a safety moment related to what it is that we're going to be talking about. And our safety moment today, I've entitled this, Anomalies Matter. Now, as line workers or linemen, even as trainers or safety people, we may not know what goes into the development of the materials and tools that we use. For instance, what do you know about the evolution of line hose? What do you know about the evolution of plastics for cover? What do you know about the evolution of the fuses that we use, or the insulators that we use, or the ropes even that we use? Well, we know what the limitations are because the manufacturer has the limitations usually clearly annotated somewhere on a tag. For instance, they might have a plastic that says 72,000 volts line to line. That's the limitation. Well, that is all the information that we need to know. The issue is, and what we find in the consulting industry, is that users will think that they understand the purpose of the tool that they're working with, and then they will use it in excess of the limitations that the manufacturer has listed for their equipment. And when that happens, that equipment fails. And when that equipment fails, people get hurt. Damage is done. So what we have to do is to train our people and to understand ourselves that we may not know the underlying science or engineers or development that went into the product that we're using, but all the information that we need in order to use that piece of equipment successfully is right there on that label. So when things don't happen like they're supposed to, that's an anomaly. And we don't want to create those anomalies by doing things that we're not supposed to do or use. And I'm going to tell you the reason why this becomes important to me, because there was an anomaly early in my career when I was a bare hand lineman. I wasn't on this site. I was about 4 miles away. But a crew had a problem with a chattering tool circuit on a bare hand bucket, and they had the bucket engaged, and when they had the bucket on the line, the tool circuit chattered. Well, they found out that if they turned the valve that closed down the hydraulics on that chattering circuit, that the chattering would stop, and they thought that that was the solution. They turned the valve, they closed down the pressure. But what they did not understand was the nature of what's called hydraulic vacuum, which we now have protections on bare hand buckets to ensure that this doesn't happen again. But when they raised that boom and they created a draw on the hydraulics, those hydraulics on that closed valve had no pressure against them. The hydraulics started to suck down the boom. It created a vacuum, and when that vacuum got between the energized bucket and the lower boom, that whole upper section of the boom flashed over at 500 kV, and it killed one lineman and permanently injured the other one that was in the bucket. Nobody knew what the issues were, but everybody knew that if something was different than it was supposed to be, we stop. Nobody stopped. They thought they had the solution because, innocently enough, they thought they understood what the issues were. This is an extreme example of what can go wrong when we have an anomaly, but it's a very, very good lesson that we all need to remember. Anomalies should be questioned. Anomalies should shut down your work. Anomalies should be solved before we continue to use and do that work. So hopefully that is useful to you, and it's really kind of related to some of the stuff that we're going to be talking about today. Our guest today is, I just can't get over the fact that I have had the opportunity over the past decade to get to know Dr. George Gela. And he is our guest today, and we're going to have a talk about some of the things that we have done together. But you actually don't know that you probably know Dr. Gela's work extensively, because if you go and you look at consensus standards that run our industry, you will see his name throughout. And for decades now, he has had a significant role in developing largely the safety and the practices that we do in the industry. So Dr. George Gela, thank you for being with us today, and tell us a little bit about your background.
Thank you. I enjoyed the interaction. So if there are any questions, please ask. Just a few words about me. I finished University of Toronto in Canada, bachelor's degree, master's degree, PhD, and then I spent some time in an industry, manufacture of large coils, air-cooled coils, reactors, line reactors, line traps, power factor correction reactors, and so on. So coils, basically. Then I moved to the Ohio State University in Columbus, Ohio, where I taught courses in power, high voltage, corona, and power electronics already. That was in 1980s. But we had the courses in power electronics, and I was part of the faculty teaching them. In 1990, I had an opportunity to move from Columbus to where we live now, Pittsfield, Massachusetts, western end of Massachusetts, a position, a research engineer with, at that time, it was GE. GE built a large transformers in Pittsfield, and in addition, the GE built a large outdoor laboratory just south of Pittsfield in Lenox with capabilities up to 1.6 million volts AC plus minus 800 kV DC, impulse 5.6 million volts. So it was a nice toys that I had the chance to play with. But even more importantly, I had an opportunity to work every day with technicians, linemen, and the high voltage equipment and engineers. We had a number of visitors. After that, I left in 2014, and now I'm a consultant. I have a consulting firm. Throughout the 1980s, 1970s, 1980s, I served as a chair of IEC Electrotechnical International Electrotechnical Commission, Technical Committee 78, which is live working, for 21 years, and then the IEC said, okay, that's enough, give somebody else an opportunity. So I left, and I was immediately promoted to the position of vice chair, because the new chair needed some help. And now I am the advisor for U.S. National Committee Technical Advisory Group for TC78, and also for 129, which is a new committee looking at building, design, or not designing, but formulating requirements for lifting equipment, equipment that can be used in the substation also, and there are significant differences in usage of mechanical equipment in the substation as compared to lines, and we'll talk about that a little bit later. And also, because I spent quite a bit of time in Canada, I was also asked to help the Canadian National Committee for Technical Committee for Live Working, to help them with their work. So I'm busy now.
Yeah, and in a very broad background in what some might consider some extraneous or outside issues. You were talking about your early career dealing with reactors and line traps. And I recall when I was growing up in my apprenticeship and we were doing some technical training during my apprenticeship, we actually had an explanation from our teacher that, well, this is a reactor and this is a line trap when we were talking about substation. And they said, you really don't need to know about these, what they do because it's very technical. But what I have found out, especially in the last 15 years, I have had probably a half a dozen fatal incidents with people that were working on or with line traps or working on or switching reactors, not recognizing what it was that they were working with. So I have since then, and what we do at ISPC, when we do training, we do talk about the technical aspects of how this equipment is used, because we want people to know, especially like, for instance, capacitor banks. I find a lot of linemen, and they won't admit this, they're simply scared of capacitor banks. So when we do capacitor training with our apprentices, we actually drain them, cut the tops off of them, open them, and disassemble them and say, see, this is all it is, and this is how it works. So that's the reason why you have been so valuable to me, because when I have come across some of these highly technical aspects of some of the investigations or research or even consulting that we do, you've been very useful to me. And by the way, Dr. Gela also sponsored me to sit on a couple of these committees. I've retired off of them now because I just simply couldn't put the time in that I needed to do that. But I sat on that TC78 and also a member of SIGRE. And one of the aspects of you as a listener is that you are the people who do this work. And one of the things that's missing on a lot of these committees is input from the people that do this work. We have a lot of very technical people that have very good backgrounds and very sound technical experience and input, but a lot of times they miss exactly how we employ and how we do this work out there. So I encourage you listeners to look into becoming getting on these committees. Dr. Gela, how does one get on a committee if they want to be involved?
Well, almost everybody is familiar with IEEE, ASTM, ANSI, and so on. I've been involved with IEC, which is international, since probably middle 1960s. Okay, and IEC is a totally different organization. It prepares standards, requirements for various devices. In live working, it's hot sticks, ladders, bucket trucks, they're called MUPs, mobile elevating work platforms. Requirements for those test requirements. Basically, it is all for manufacturers, but we need input from the actual people who are going to use it. And one example, and it was not at TC78, one example is that there was a suggestion to develop something to replace hot sticks. Because hot sticks are long, heavy, and if you're talking about 1,000 kV, million volt lines, those sticks can be very, very, very long. So that means that you have to longer trucks, bucket trucks. You need support. They're heavy, and there was a suggestion to develop flexible, something like, it's not a rope, but something similar. And I was asked by IEEE Power Engineering Society Transmission Distribution section to sit in as a guest, no voting rights, but sit in as a guest. And during one session, we're discussing the requirements for this flexible, what they call the flexible hot stick. And I asked, I did not want to embarrass anybody, but I asked a question. It's made of plastic, whether it's nylon or Kevlar or whatever, plastic tends to elongate under stress. So if you're going to replace insulators with hot sticks, the hot sticks are rigid, you have an adjustable pin at the top of the insulator, you crank it up and release tension on the insulated string. When you try to do that with something that can elongate under stress, how much elongation are we going to allow? The answer was, took some time to discuss, but the answer was 10%. So I said, okay, if we have, let's say, in round numbers, we have a 10-meter long insulator string on a 1600 kV line, which is just an estimate, as an example. And it will stretch, this device will stretch by 10%. How are you going to release tension on the string? If you use a 10-meter flexible string, it will stretch to 11 meters. So it will not release tension on the insulator. You cannot remove it. If you try to use a 9-meter flexible tool, how then are you going to attach it to both ends of the insulator string? So after a long discussion, and I have to admit that many people on that committee developing this product did not have practical experience. Okay, and after a long discussion, several years actually, I think the decision was made to change the composition of the plastic and allow elongation of 2%, which is still significant, but with a hot stick, also adjustable hot stick, you can take care of that. So it's important to have input from both the highly tactical people and the hands-on.
Yeah, and we have recently, you and I have been on a committee that is helping to standardize the suits that bare hand workers wear. And one of the issues that I've had, and I think this is a very, very good example of why we need users on these committees, is because the evolution of the suits, which has been driven by the manufacturers of the suits, has gone into an area that really concerns me, and that has to do with the very heavy input of the Europeans, which this is going to be an international standard that will eventually affect the work that we do in the U.S. One of their concerns is the health risk of magnetic exposures or exposures to induction. And one of the issues that they are discussing is when workers should be wearing these suits. And it has boiled down to that there are some people that think that when you walk out into a substation yard in that fence, you should be in a protective garment that will protect you from the exposure to induction. And I think that a lot of people that are in our industry, especially working out in places like Texas and in Florida where the temperature gets up to 114 and 98% humidity, have a concern about wearing a full suit and just simply to walk through a substation because of the exposure. What do you think about that?
Well, that is driven by publication that ICNIRP, which was published probably 20 years ago or so. I don't remember the date. I have it, and we discussed this, and it specifies limits, exposure limits, which are a function of the value of the electric field or magnetic field and the duration of exposure for general public and also for live working linemen involved in contacting the conductor. Now we have to remember that linemen are and should be and are trained in how to not minimize the magnetic or electric field, but how to deal with it. Okay, and I just came back from a third training session in Northeast in Maine, and my wife wasn't very happy because she could not see a moose in that area. and she came with me. But I like to when I do the training, I have mock-ups of towers, maybe 24 inches tall, metal, that somebody from Venezuela gave me. 2 towers, and I put the conductors, 3-phase conductors, and show, for example, things like sag. And then I have a bucket truck that my daughter bought me, a toy. Then I bring that in and show various locations, how to position the bucket, how not to position the bucket, what it means, and coming back to conductive suits. Your point about the heat exhaustion is very, very well taken. There is, okay, a few steps back. Conductive suits have been around. When I joined Lennox in 1990, there was a researcher from Canada that spent about a year before I joined and actually tested conductive suits in high voltage and high current environment. When he left, that was not published for whatever reason. So I took his notes, acknowledged him in the publication, and published 1 or 2 reports on use of conductive suits, performance of conductive suits, of the person in a bucket truck, in a steel bucket, no bucket, and measuring exposure, measuring field levels, electric and magnetic field levels at various locations on the body. We employed Smokey Joe, a mannequin, Smokey Joe, and also Chicken Charlie. Chicken Charlie was based on an engineer from Ohio Brass who was very tall and very, very heavy. So we decided to make the Chicken Charlie the largest possible, okay, to occupy the largest space near the conductor. Smokey Joe was a mannequin covered with painted with silver paint for conductivity, so that we could measure current underneath the conductive suit. What we found, or what they found before I came, and then I included that in the report, the worst area, the most sensitive area on the body, any guesses? Around the neck. Why? Because you have to move around. You're not up on the line just for fun. You have to move around, and the collar moves and makes contact and breaks contact. And it's not dangerous. That will not cause electrocution, but it is disturbing. It is uncomfortable. So the new suits, several years ago, new suits were developed and proposed and sold, and they are, you're right, they are very heavy, thick, and so on. Do they meet the EPRI requirements and also NC requirements, and some other countries have their own requirements? Well, that's what we're trying to determine. See what happens. But the suits, the idea behind the suit, and I was not involved in the development. I was just providing, some input. The idea of the suit was to shield the body from electric field, shield the body from magnetic field, and also provide a path for a current in case of heavy currents involved. Well, if you expect a heavy current through your body, then that means that the other protection on the system is not working properly, either grounding or whatever. Okay, there are several layers in any job, on an electrical job. There are several layers of protection, prevention. Number one is proper design. Number 2 is training. Number 3 is maybe special equipment like gloves and suits and so on. The last one is control of over voltages and over currents. And that's one thing, and I'm slowly moving to my pet peeve. During training, I emphasize to the lineman that it's not the hot stick, it's not the suit that protects you. That's not the first line of protection. The first line of protection is proper design, proper use, and understanding of what may be happening, what may happen. Okay, and I think we're reaching that point. The last level of protection is PPE.
And thinking back, I topped out in bare hand training in the 80s. And the issue then was also nobody in the U.S. was making suits. They were all coming from Europe, and nobody was making a suit for a 6'3", 270-pound lineman, and that was me. And they were tight, but the material was almost like a handkerchief thickness. And then they came with hoods, and I could pull the hood over my head, but the front of my face was not shrouded, and I'd actually get a little bit of a sunburn, on my nose, because of apparently it had something to do with some sort of magnetic arcing or something that was going across between the outside rim of the suits. So I was constantly pulling that down. But like you said, we were trained to recognize that preparation, measurement, quality of bonding, all of those things were the precursors that were going to prevent the kind of incidents that would flash over a bucket or flash over a man. Now, thinking of the limitations too of what we were talking about, I called you once when I was going to consulting with a company, and it's kind of funny because they had been doing de-energized transmission work for one of their clients, and they bid an energized transmission job, and they had never done energized transmission, and they got the job. And so they called us for some help, and they said, we think we know what we're doing, but we need somebody to help us make sure that we're doing the right plans, and we want to do some training, and we'd like you to come out and like you to run the first 2 or 3 transfers that we're going to do. And so that's what we did, and that's how we quoted it. And when I got out to the job site, the crews were, if you remember, this was 115 kV, and they were pulling out plastics, and they had plastics that were rated at 72 kV, guarded phase to guarded phase. And they were going to put plastics on the conductors because they thought that the plastics, it was 115 kV, so they were thinking phase to ground being about 60 kV, something like that, which, by the way, there's an issue with delta transmission thinking that you actually have a limitation of voltage and phase to ground, because you don't. If you actually have a phase to ground fault, that phase to ground fault voltage is going to be considerably higher than that multiplied at 1.73. But anyway, they got out these plastics. I knew this was wrong. I knew that it wasn't right, but I couldn't really create an argument because I didn't know what the limitations were. So I called you, and what did you tell me about plastics and limits?
Well, several things. One, I just did some calculations before we met. 115 kV divided by square root of 3, so the line to ground voltage is 66.4 kV. So you would think that 72 kV plastic is good. Well, how does that 72.4 or 72 kV come about? It's only either calculation, which I would not bet my life on calculations, and tests. My job for many years, at 24 years in Lennox, was to test things to destruction, test things to determine margins, safety levels, and so on. So 72 kV cover-up. I was asked whether we can actually use it on 115 kV or at least 69 kV. Well, it's not only the voltage rating, it's other aspects. For for let's say 45 kV, you could, or 69 kV, you could put 2 line houses end to end. The problem is not that, but the problem is that there's a gap between the two. If you make the line hose twice as long in one piece, then, and we tested that, then you need at least 2 hot sticks and 2 people to install it. And it's very difficult, that would be a 6-7 foot, maybe 10 foot long hose, which is not very heavy. Holding it, installing it during strong wind, is very difficult. Okay, so from electrical point of view, it may be possible, but from the practical point of view, it's not advisable. And I was very fortunate to have the opportunity to work on both practical and electrical. Okay, 72.5 kV is more than 66, and 115 divided by square root of 3, which is line to ground, is less than 72. How do you install it? Okay, you have to install it either on the outside phases. You can install it from the outside. On the middle phase, especially on delta, how do you install it? That's a problem. And in the case of some wind, that line hose or that the piece of equipment is difficult to control. Okay.
And there you go. And didn't you have them flash over at some limit too when you were testing those plastics?
Yes. For the we tested it with AC, with DC, and with switching surge. Lighting is not an issue for live working specifically. For design, yes, it is, but for live working, it is not, because we do not do live work in thunderstorms. And if a lightning hits a line, and I'm digressing a little bit, but if a lightning hits the line, the surge, high voltage surge, will propagate down the line, and when it propagates for about 10 miles, 5 to 10 miles, it will look like a switching surge. Okay, that's where this famous 5 to 10 line mile rule comes from. That was based on tests here in Northeast, long time ago. That was published in AIEE, the predecessor of IEEE. And if anyone would like to have that report, I have it. It's a paper that was published, and discussions. Lightning is not considered an issue in live working. Okay, because we know what happens when the lightning hits the line far away, and we stop work, or should stop work, if there is lightning in the area. We were asked to test end to end those line hoses or those spiral covers, and again, as I mentioned before, one of those is not long enough. 2 end to end, you still cannot avoid that junction, and surge will find its way along the surface of that cover up and find its way through the gap between the two.
Yeah, and you may get away with it if it's hanging out in the middle of the span, but one of those plastics is going to be up there against those insulators on that dead end or against that suspension, and now when you bring that plastic up there, you're in contact with a path to ground across that insulator. And at the time that we were working on this project that we're talking about, we weren't concerned about TOV, which is another issue that a lot of people don't truly very well understand. TOV is switching surges, and so you may get away with that 66 to 72 gap and saying, hey, that'll be enough, but you get a TOV that ends up 3 to 5 times of what that circuit voltage is. That plastic is way out of limits in protection. So what it boils down to is you given us a really good observation of what went into those limits on that plastic. So what we're telling linemen is there's a label on that plastic for a reason. And when it says 72 kV guarded phase to guarded phase, that's not 115 to ground, because you can put plastics on 69. But what we would rather do is just have very good sticking quality and practices that will give us exactly what we need when it comes to protection for those.
Attention all utility professionals. Are you ready to transform your safety leadership culture? Introducing IP Institute's Frontline Leadership Program, a comprehensive training program that will elevate safety throughout every level of your organization. Led by one of the industry's premier leading minds, David McPeak, this program offers in-depth modules on leadership, human performance, and incident prevention. Frontline delivers key safety problem-solving skills, either in person, in an engaging, interactive classroom session, or learners can become safety superstars through our convenient video-driven online course. Don't miss your opportunity to take your organization's safety culture to the next level. Go to ip-institute.com and join the thousands who have built a powerful, sustainable safety culture with Frontline.
You and I have done a couple of legal cases over the years, and one of them, I was very good at explaining why this plaintiff against this utility was wrong. They were moving a sign on a highway into position, and it was very near a right-of-way that had 6, I think, transmission circuits in there, anywhere from 69 to 500 kV. And as they swung the sign in, the sign got loaded up with some electrical induction charge. And the electrician who was catching it when it was being boomed in received a shock. And he had seen on television exactly what happens when you get shocked, and he went into these convulsions and screams and saying he was electrocuted. And I got involved, and I found out that sign was suspended on nylon slings from a crane. So what that meant was it was simply an isolated conductive surface that was going to have a capacitive coupled charge on it, but it wasn't going to have any current because it wasn't part of a loop or a system or a pathway. And so even though he may have gotten shocked, he wasn't electrocuted, and he was claiming that he had neurological problems, could no longer work, and all that other kind of good stuff. But as it turns out, me as a old lineman telling a story, it may make sense, but somebody was going to have to do the technical aspects. And I got you stuck into a calculation for induction that was almost outrageous. Tell us how that works.
Well, how that works is just a few steps back. You are standing under a transmission line, let's say for round numbers, 500 kV line. You are standing on ground. What's the voltage on the ground? 0. Okay? Now, how does the voltage change from the 500 kV divided by square root of 3 in the details, but from a high voltage energized line down to 0 on the ground? If you're on the ground and you point, I always tell my kids, don't point at the line because it might point back at you. If you point at the line, you may feel a little sensation at the end of your finger. Okay? That could be corona, although it's most of the time it's not, but that is a simple fact that voltage has to change somehow from the high voltage line, energized conductor, down to ground. It just doesn't happen in zero distance. And what many people do not acknowledge and do not understand really is that voltage is a derived parameter. It is not this fundamental quantity of electricity. It is the electric field. Same with magnetic field. Magnetic field, there's a different terminology, but basically electric field is a vector in space, and if you stand under a transmission, a high voltage conductor, directly under, then the electric field is strong at the conductor level, close to the conductor, and it still exists near ground and on ground, and it points vertically down, okay, on AC. On DC it would be either up or down depending on the polarity of the conductor. Now, if you move away from the conductor along the ground, it still has to be at ground. The electric field vector has to be perpendicular to ground, because, according to Mr. Faraday, who's our very, very nice colleague, said and proved that electric field must be perpendicular to a conductive surface. Okay? Otherwise, if it is not perpendicular, then there would have to be a voltage difference between the points in one location and another. That means that the conductor would not be an equipotential surface. A metallic conductor, metallic objects are equipotential surfaces. So that sign that you mentioned was a metallic object, or it was in a metallic frame, and so on. At every location on that object, the electric field had to be perpendicular to the surface of that object. Okay, so if you have a sign that's, let's say, 10 feet tall, the entire sign is at some voltage. We call it induced voltage, space potential. Okay, and that means that the top of that object is physically closer to the line, so the field there must be stronger, and the bottom is closer to ground, so the field there must be lower. Okay, but the entire frame has to be at the same potential. So when that person touched the object, the sign, the sign was actually electrically charged by the electric field. And it was not a continuous spark through the person, but it was a shock. Okay. Similarly, with magnetic fields, it's a little bit more difficult, because magnetic fields are not lines of force, but contours of force, closed contours. So mathematics are a little bit more expensive. But why do we see? Why do we get the shock when you're under a line and you touch, let's say, a vehicle? The vehicle now, vehicles today have rubber tires. Some time ago, several decades ago, the tires were rubber without steel reinforcing. Okay, so they were not steel-belted tires, and many linemen got a shock when touching the vehicle under a line. Now those vehicles have steel-belted tires, so there is a better contact with ground, so the vehicle is more likely to be closer to ground in voltage than 50, 60 years ago.
But the lineman standing there creates a charge, and actually the body becomes charged, and now he touches the vehicle at a different potential, receives a shock, and believes that it came from the vehicle, when it was actually a discharge of his body voltage into the vehicle that was at closer to ground potential.
That's right. And that is even worse now than, let's say, 50 years ago, because the body of the vehicle is now better grounded. In the past it was better isolated. Now it is better grounded, but it's a much larger object. So the charge on the object is much larger than on the person.
Yeah, and there's some utilities that simply won't tolerate even that kind of electrical shock, because one of the things that people don't realize is that is capacitive coupling. It has no element of current flowing with it, and we always ask the question, what kills you, the voltage or the current? Everybody knows it's the current that kills you. There are some exceptions for very high charges with people that may have some other conditions, but the fact is that you're going to touch the vehicle, you're going to get really shocked, and everybody's going to laugh at you for a real long time. You're not likely to get killed, but you probably won't do it again.
Yep. And remember not to do it again.
Yes, exactly. The last thing that I want you to talk about is that you and I worked on a case that I discovered through Incident Prevention Magazine, which is part of that UPM, our sponsors. And it was a story that actually was from a different perspective, but it was related to an incident at a utility out in Arizona that had a brand new out-of-the-box bare hand bucket truck, and they ran that bucket up in the air inside of a substation, and within just a few minutes, they had a flashover of the upper boom and destroyed the truck. Nobody was hurt. And that was a good thing. But when they wrote the story, they were talking about perspective from something else. And I called the utility up. I knew the guy that was involved. And I said, I have an experience. When I was a foreman on a bare hand crew and I had a bucket, that if we were near a substation or in a substation, which isn't unusual, that because it was the bucket that I ran every day on the same voltages all the time, we knew exactly what to expect on leakage. But when we were near a substation, it was never what we expected. Sometimes it was high, sometimes it was low. It was really weird, but remember, I grew up with that concern about anomalies. So we found out that if we stayed outside the fence and we were at a right angle to the conductor, we had an expected and reliable leakage, and we just simply wouldn't ever work in a substation. And I had always taught when I started teaching bare hand that we shouldn't be putting booms up in a substation. I didn't know why. Now we had this flashover, so I got Dr. Gela involved, and Dr. Gela started doing some research, and he actually came up with the solution to what most likely happened that actually solves a whole bunch of problems that have been occurring worldwide in similar circumstances. Tell us what happened there, Dr. Gela.
Okay, that was a 500 kV switchyard, not even a substation, but switchyard. The difference is that in a substation you have different voltage levels. In a switchyard, all equipment was 500 kV. Okay, and there are other ways to do work in a switchyard or substation, but that utility brought in the bucket truck into the switchyard, and per procedures, okay, A92.2, you're supposed to touch the bucket without anybody in it, touch the bucket to the conductor, and measure the leakage current. Okay, that is the last step, last safety check. And what they did that. There was a person standing on the truck, or the controlling the lower adjustments, and he raised the boom, the bucket to the conductor, made contact with the conductor, observed the current of something like 124 microamps, if I remember correctly, which is well within limits for 500 kV. Within half a minute or a minute, the current increased to the 17 microamps, and then almost instantaneously, boom, the arm flashed. Okay, and no injuries, but the arm was damaged, and significantly damaged. The bucket truck was tested at BPA. It was tested in other laboratories. And the boom was damaged, but there was no other significant damage on the chassis. I visited the yard, and there was damage to the fencing, arcing. Okay, so what caused it? Several things. And I started thinking about it, talking with several people also. And the first thing I noticed is that the distances, conductor height, face-to-face distances in a switchyard buswork are smaller than on a transmission line. We have a lot of experience of using bucket trucks on transmission lines. In a substation, all those distances are smaller because rigid busworks don't swing, don't sag, and you do not have the all the requirements, the swing angle, how close it can be to the tower, and so on. And I always emphasize that there is a significant difference between distance and the clearance. If you talk to a design engineer, the design engineer will talk about clearances. Okay. And the clearance on a transmission tower is have a minimum value at maximum the swing angle of the insulated string, which is something like 15-20 degrees. Okay, for live work, we do not work in high winds, so that the distance to the tower is much less than, but greater than the required clearance. That's why we distinguish between distance, minimum approach distance, and clearance. We work with distances. The other thing is that the design engineer, if you have a bundle conductor, 18-inch bundle spacing, the distance, the clearance, is from the center of the bundle to the tower. Okay? Well, if you are working on a line, energized line, if you're a lineman, you have to consider the fact that you are now at least 9 inches closer to the conductor than the designed distance. Okay, so that's something that again we have to emphasize, and I mentioned that by showing it on the mock-up towers. Okay, and finally, what is important is the electric field again, and that may be difficult to visualize, difficult to show, but it is the electric field that's important. And the electric field in the transmission line is produced by the tower, yes, the grounded tower, but also 3 conductors, or if it's a double circuit line, 6 bundles. And usually the electric field, which is a vector, electric field lines are fairly well known. In a switch yard, there are towers, metal towers, there are transformers, there are crisscrossing energized wires. So the electric field environment is very, very complicated. Okay, and it took us a while to absorb that and analyze that and focus on that, and what the cause, we think, cause of the flashover was corona. Corona not only at the top of the boom, where usually you have a corona ring, but also at the bottom of the insulating portion of the boom. And the insulating portion of the boom is usually at the ground potential anyway. So when I mentioned that, that was at the IEEE meeting, everybody said, well, there's no corona on the grounded conductors. There's no corona on the ground. So I showed several things, like St. Elmo's fire on a ship. Many ships burned down in the sea because when clouds were thunder clouds were close by and low elevation. But the ship is grounded. It's in a sea salt. Okay? Years ago, there were instances where in the military, a helicopter was carrying some load, lowering the load, and the servicemen on the ground grabbed the load to steady it, and actually figures were blown off because of the electric field. Again, at corona. Another example is if you go under transmission line and look at grass or look at trees close by, you will find that the leaves are burnt, and that's because of corona. Now, what corona is it's a discharge in air, a very small distance, but the discharge in air, ionization of air, and what we actually see is not the corona itself, but the result of corona. Okay, so once we realized that, I floated that idea with the person in charge of the research at that utility, and he needed convincing. Didn't disbelieve me, but needed a bit more convincing. So we did calculations, and what it showed is that the profile of electric field not the vector, but the electric field magnitude, which is a vector consists of three components. So the magnitude of the electric field along the insulating portion of the boom changes and concentrates, increases at both ends of the boom. One at the corona ring close to the bucket, and the other end, which is at ground, it's connected to ground, and it is close to ground. At that point, it also a high electric field can exist. And once you have high electric field, that what probably happened is corona at both ends occurred, and either because of wind or just because there was corona and movement of ions, it flashed over.
Yep, ionized air created a conductive cloud, and by the time both ends got together in the middle, created a flashover path. So you had to spark over, and then once you had to spark over an ionized air, then there was a flashover. So it may actually result in the future that we may find out we're going to have corona rings on both ends of the boom, depending on how we use those trucks. But what we're saying, and what Dr. Gela's results said, is we ought to find a different way to do inside of a switchyard, a high voltage, a transmission switchyards. There are insulated scaffolds that can be used. I've used them before, and I've had my crews use them. And just because you have a truck, it's not necessarily the way you're going to do it. You just need to understand that these principles exist. And one of the things that I remember hearing from the utility when I said, hey, I think this has something to do with induction, but I don't know the technical aspects of it. They said, oh, no, we were way outside of MAD, because what they thought was that MAD and induction were related. So if they had created, let's say MAD was 4 feet, they were thinking that once they were outside of MAD that they didn't have any effect that may be detrimental to the boom, not realizing they were not the same thing. So in this case, here's some anomalies again that helped us to determine what the actual risk might be. And that one little incident with the right people getting involved probably is going to have a positive effect on the safety of the whole industry from that particular aspect. So I hope that you, the listeners, have learned some things today about some technical aspects that you may never have considered. If you need help with answering some questions that might have come up, you know how to get a hold of me at ISPC, which is Jim at ispconline.com. Love to hear from you.
IP Institute's Frontline program, empowering utility professionals to lead with confidence and safety. Visit ip-institute.com to start your journey today.
So, Dr. Gela, do you have any other final comments you'd like to close before we say bye?
Well, thank you very much for the opportunity. And one thing that I would like to emphasize is that everything that we do, and I'm involved in IEEE standards, ISTM, NC, IEC, everything that we do is based on actual full-scale tests. That's why I was very fortunate and very glad to end up in Lennox, in the Lennox lab, where I actually had to do tests on hot sticks, electrical tests, and also mechanical tests on trunnions, because that's another problem that people have not realized for a long time. We know that trunnion used to have a very short neck. Now, if you look at A.B. Chan's, what used to be A.B. Chan's products, it has a much longer neck because it used to pull out. Okay, and other things, cover-up equipment, substations. You mentioned substations, using conductive soutes in substations. Well, that's fine, but we also require, at least some utilities require, conductive boots or insulating boots. Well, but you go to a substation in a rubber boot, step over the crushed rock, and that will puncture the rubber. Okay, or the insulating boot has to be properly designed. Not because the manufacturer wants to sell it, but because you are standing on the ground and there are mechanical stresses on the footwear that are not important or do not exist anywhere else on the suit.
And what we're talking about here is the big picture. There is a lot bigger picture than that tool that you're handling in your hand. And I think one of the things that tells us is that linemen, these workers in the field, have value to the evolution of safety in our industry, but only if you bring it up. So when you find things that raise questions, ask the people that can give you the answers, and let's find out what it is that's going on. So thank you very much, Dr. Gela, and looking forward to seeing the more evolution of safety and training within our industry. You have been a great asset to the industry. I want to thank you very much for doing that. So for those of you who've been here, thank you very much for joining us, and we look forward to seeing you next time. And we also want to remind you to join with our sponsors and look at their products, and we'll see you next time.